In this lesson, we're going to go back to data and look at scatter plots again, but this time using some technology to do most of the work for us. So we've learned how to make scatter plots, did lines of best fit, we interpolated, we extrapolated, they were okay. What we really want to do is we want to have a consistent answer with all the same answer, because mathematically it makes a little more sense. So going back for a second, talk about correlation. Okay. We had positive correlations, graphs that went up. We had negative correlation, graphs that went down, or of course we had no correlation, no pattern at all. That was okay, it was a good start. But in addition to classifying the shape of your dots, we actually want to know how good is our interpretations, how good is our predictions, how good is that line of best fit. So to do that, we're going to add a word in here. We're going to have three types of correlations. So for instance, this first one here, yes, it's positive, it's going up to the right. If you actually look at the dots, some of the dots are way above the line, some of the dots are way below the line. These dots, yes, are going up to the right, but the dots are spread out quite a bit, so we call that a weak correlation. The second one, you could have a negative, obviously they're going down to the right, but the dots are a little bit closer to the line. Actually, they're pretty close to the line most of the cases. There's very few that are far from the line. We call that a moderate correlation. And the last one, again, it's positive. It's going up to the right. The dots are really close to that line. In fact, a lot of dots are on that line. So we call this a strong correlation. Now you might be asking yourself, how are we going to do this if it's still looking at it with our own eyes? How do we judge how far those dots are off? Well, we can use this is where technology comes into place. We won't have to do that. We're going to at our computers or phones if we need to find our R value. The R value, which is called Pearson's correlation coefficient, actually tells us how good this model is. And here's the kind of numbers you can get. So if you got an R value of 0, that means there is no relationship whatsoever, no correlation. The 4 dots, the 6 dots, the 8 dots, there's no pattern here whatsoever. You won't see that very often. You could also get an R value of 1, which would be a perfectly straight relationship. All the dots line up perfectly straight. Now, each of these R values could also have a sign. So if you had a negative 1, the negative tells me the graph is going down, and the 1 would be a perfectly straight line. We probably won't see that very often either. What we will see is values that fit into these categories. We're going to really just break them into thirds. Okay. So if you got an R value of negative 0.2, well, the negative tells me it's going down to the right, and the 0.2, which fits into this interval, tells me it's weak. We don't really like weak ones. What we're hoping for is a nice, strong relationship. It could be positive or negative, but we want something, hopefully, I don't know, 0.9, 0.8, something pretty strong. So if we saw something like this, 0.95, it would be a positive relationship going up to the right, and they're not quite in a straight line. Maybe you have one that's a little bit off like that, or a little bit off like that. They're almost all in a straight line. That means we'll have some really good predictions, interpolations, extrapolations. So the question is, how do we get these things? Well, to get these things, we need some technology. So we're going to grab our computers, we're going to open a tab, and we're going to type in the word Desmos. If we do that, it brings up this screen here. We're going to open the graphing calculator, and here's our screen. Okay, so once we have Desmos up, we are going to go back to our question, and we're going to try and use technology to help us solve this problem. So we have a lab technician. They model the growth of bacteria by scanning it every hour. The number of bacteria is shown. So in the past, we had to make a graph by hand. We'd have to pick a scale, follow our dots, and do all these fun things. We're going to use technology to help us do this. So how do we do this? Let's make this smaller so we can see the question. Okay, we want to put all this data in here. So we're going to put the plus sign, and we're going to pick table. You can type your table in just the way it looks. If you make a mistake like I did there, you can just go back up to it, type over top of it. Easy to work. You can go to the right column, go to the top, make sure that you match up the right data with the right data. That's the only trick, I suppose. And you should have the same number of things in each column. Just check your numbers, make sure they look good, and we should be good. Okay, notice when I make a biggie and you don't actually see any of the data. It's not because it's not there, it's because my scale only goes from -10 to +10, and from -10 to +10, look where our data is. If I actually drag this down a little bit, you can see the first dot, and that's 1 and 10. But I don't want to drag it, so what other tools do we have? Well, up here, we can zoom out and see all our dots. But if you notice, as I zoom, it zooms both directions at once. So my scale is 600 here and 600 up there. Doesn't really help me see this data. We don't really want these two scales to match. So to fix that, we're going to go to our wrench. Our wrench is our graph settings. The x-axis is my first thing. I want to see 1 through 7. I'm going to make it a little bit bigger than that. I'm going to go from 0 to 10. My Y scale, I'm going to start at 0 also. And I'm going to put this up to 500. Okay, and if I want to put the wrench away, just click on the wrench again. You can see there's all our data. Now, by putting it at 0, I can't actually see 0. It's right there. You can't tell, but it's right there. So I just usually drag it up just a little bit so you can see it. Okay, we can also add headings to this. If we go back to our wrench, it says the word label right here. So our labels for this one are time and bacteria. So I'm going to take those words in here, time, and it was in hours, and bacteria. And notice it comes up as you're typing. Let's put that wrench away. And here is our beautiful scatter plot. Let's answer some questions. So part A says create it, did that. Classify the linear correlation. So just looking at the dots, you can tell it's a positive one. But we want to find that R value to say how strong is that positive correlation. To do that, up here you might notice it says the word add regression. It also looks like a, I don't know, scatter plot with a line best fit on it. If you click that, it puts the line best fit on for you. And the R value that we want is actually down here at the bottom, right there, 0.9269. So let's write that down. A, we did it. The R value was 0.9269. Okay. This is a positive correlation, went up to the right. And this number fits into 9292, fits into this interval right here. So that means it's going to be a strong correlation. Okay, so we did this part. We found the correlation coefficient. I guess it's actually part B. And you want to find the equation of the line best fit. So in the past, we just drew it on. But now we can actually write an equation for this. The equation is y equals. You can get the rest of the equation by looking right here where it says the word equation. We're going to take this guy and we're going to round it off to 2 decimals. So 75.64. And it had an x attached to it. And then it was minus 142.71. What the line of best fit equation is telling us is, it's saying y, which in this case was bacteria, is 75.64 times x. X is my number of hours. And then I have to subtract 142.71. So what it's telling us is we can calculate how many bacteria we have based on this equation. All we have to do is fill in the number of hours, and we can get the number of bacteria, which means I can interpolate and extrapolate pretty accurately. Part C here, based on our line of best fit, so based on this, how many bacteria would you expect after 10 hours? So I could put 10 in here and use my calculator, which is totally fine, it's pretty good, but why not let the technology do the work for us? So if you go back to decimals for a second, we're going to go down to number 2 here, it says, and we're going to type that in. I wonder what happens when x is 10. Now notice nothing happened on my graph because, again, my scale, 2, 4, 6, 8, 10's right here to the side. If I drag it over just a little bit, you can see the line at 10. And if I zoom out just a little bit, you can see where it hits my line best fit. If you click where they hit, it actually brings up a gray dot. Can you see it right there? If I click it, it tells me what the value is. So 613.71. 613.71 bacteria. Now, I guess you can't really have part of a bacteria, so let's round that off to 614 bacteria at 10 hours. That would be an example of extrapolation because we've gone beyond our data. Okay, that's how Desmos works. We're going to try another one just so we can keep practicing with this. Okay, let's try the next one. We got Talia. She planted some bean seeds for an experiment. The table below shows the average height of the plants during the first 2 weeks after they germinated. Here's our data. We're going to create a scatter plot. So let's try this one together. Just actually I'll make it big still. Okay, so I need to get rid of all this stuff. To get rid of it, we could reload the page. It's totally fine. Or we could just click on the X's. There goes my line. There goes my data. And notice that it says bacteria and has the right numbers there still. If I click on home, it goes back to the normal one. But to get rid of your labels, you literally have to go back in and get rid of them. Okay, we want to put our new set of data in. So we're going to need a new table. This table is written horizontally, but we're going to put it in vertical. So my day is my independent, my X value. So I'm just going to put those in. I find the Y's that go with them. Down just a bit. Oops, I should say 10.5. Make sure that last one's at 26.8. Good. I'm going to change my wrench. My X's, I'm going to go from 0 to 15 this time. My Y's, I need to go from 0 up to, I'm going to say, I'll go past that. Let's go to 30. Yeah, I'm not going to worry about the labels. I know which ones they are. This would be my days. This would be my height. You can put them if you need to. And move it up just a little bit so I can see my 0. Actually, let's zoom out just a little bit. That looks like a pretty good line of best fit. I almost look perfect. Okay, what kind of questions are they asking us? Create a scatter plot. Done. Determine the correlation coefficient. Okay, that's our R value. Scroll down. If we look at it, we get an R of 0.9998. As I said, it looked almost perfect. And then almost a perfectly straight line there. 9998. How good is the fit? Very strong. Almost perfect. Positive correlation. Okay, part C, write down your equation. So we're just going to copy it off of here. So y equals, and give me 2 decimals, so 2.01x minus 1.4. 2.01x minus 1.4. Again, this is telling us that the height is 2.01 times however many days go by, but then you have to subtract 1.4. So it's giving us a nice equation we can use to extrapolate, interpolate. Part C, let's find the height at 10 days. Oh, sorry, at part D, height at 10 days. So we could put 10 in here and use our calculators, but let's let technology do the work for us. We're going to go back to our Desmos. We're going to put in x equals, we're going to put 10. This is an interpolation between two dots that we know. And I got 18.725. That should be a really accurate height, right? Because number one, we know we're interpolating, so it's between things we know, and we have a super strong model, which means super strong predictions. All right, part E, let's extrapolate what happens at 3 weeks. So be careful here. It says 3 weeks. Don't put in 3, because if we put in 3, what happens? Well, that's 3 days. We need 3 weeks, so let's turn that to 21 days. That's way over here. Notice it's a different color line. Actually, it's not. It's the same color line. We can change it to a different color line, though. Let's click on that and change it orange. Okay, so at 3 weeks, we get this number, 40.8625. 40.8625. I'm just going to round that one off. Okay, how accurate do you feel this value would be? Okay, now here's where you have to be a little bit careful. Not likely to be accurate. We love interpolating, especially with strong models. We don't like extrapolating, even with strong models, because you don't know what happens next. We don't know enough about the situation just to make this say it's going to be a good accurate estimate, because what could happen? Well, what if you don't water it or it gets no sunlight? That could have an effect. Well, what if these plants stop growing after 2 weeks? That could have an effect. Right? We don't have enough information, and mathematically we don't like to extrapolate beyond the end of our data. Like, you might be able to go to 50 and be pretty accurate, but anything beyond that, we say, no, let's not do that. Okay, and get you guys to try one. So this is the last one. You try this one yourselves. So pause it, try it, see what you can come up with. So we're going to get rid of our old stuff. We're going to enter in some new data. So this relationship is looking at Alex, who learned his favorite movie had grossed more than $700 million. He decided to track the box office for a new movie he liked. So this is how many weeks have gone by and how much money the box office made. That's what grossing means, making money. So create a scatter plot, did that. Let's see what it looks like. Ooh, I might need to adjust that a little bit. I'm going to do my axes. Make them go from 0 to, let's go to 20. At Y's, starts at 150. Ooh, my lowest is 1. So let's go to 150. Okay, that looks like a nice little graph there for us. So there's a negative correlation this time. And determine the correlation coefficient. Let's do that. So scatter plot. So I get an R value of negative, which makes sense. 0.9138. Negative 0.9138. So it's a negative correlation and strong. Right? Those are the two things that go together. And our line of best fit is y equals negative, let's go 2 decimals here, 8.66. And it was minus 142 point, what was that number? Oh no, 130.72. 130.72. Was it plus or minus? It was plus. Okay, so there's our equation. So it looks like it's going down by this much for every week that goes by. Yes, that's what the X and the Y stand for. How strong is this model? It looks really strong to me. It's okay that it's negative, it just means it's going down. Okay, describe the trend. Oh, sorry, those are B and C, not A and B. Okay, so our trend is using our words from our graph. So as the weeks go by, the movie grosses less money. That's why it's negative. Okay, interpolate what happens during week 5. Should be a pretty good interpolation because we have a pretty strong model. Let's just type in x equals 5. And I got 87.44. And so we got 87.44. Notice that's in dollars, but not just dollars. It's actually in millions. Make sure you put that word in there. I made 87 million, which should make sense. Week 5. It's somewhere between in here. Now, why is it less? Actually, why is it more than the 70? Well, maybe the 70 was a little bit lower than we expected. If you look at your shape, the 4 is right here. That was actually a little bit lower. Or if you stop and think about this, does the graph really look like a line? It looks more like a curve to me. So that's kind of our extension to this idea. Yes, our answers are accurate for what we know, but down the road, once we learn how to draw graphs that have curves in them, we can add other shapes to this. I haven't talked about where it said linear regression here, but if you click on this arrow, there's all different kinds of regressions you can do that may be more accurate to the situation. Okay. Notice they don't have r's anymore, they have r squared because they're curves. But really, this is probably the best model right there. Look, it goes down and it kind of levels off. Call that an exponential regression. We don't really have enough math to be able to deal with these things yet, but down the road, once we learn a little bit more about math and Desmos, we can start using some of these other tools. Okay, you guys are going to try the sheet. It's attached to this. Um, I will ask you guys about R's and interpolation, extrapolation, and lines of best fit. You may not have to use technology, but I will get the information from technology for you to use at some point. If you're stuck, come see me or send me a question.